All right, and another wave-related phenomena is diffraction. And diffraction is the bending of a wave around a boundary or an obstacle. And this picture from the book demonstrates water waves diffracting through these breakers. You can see you've got the waves coming in, passing through the opening here, and then as a result you can see these waves generated. And so these bending, spreading out waves generated by the fact that the water is passing around this obstacle or this boundary. And so with a single slit, the diffraction pattern looks something like this. It looks similar to what we have for the double slit interference, but it's not identical. Some of the differences are that the central peak is the most intense, and then these higher orders fall off considerably in intensity. It's not a gradual decrease. And so let's investigate what exactly is going on. So for a single slit, you may think, well, if there's only one slit, how could there be interference at the screen? And the idea is that since the slit has physical size, you have a bunch of waves that are passing through the slit. And when you start comparing the waves that are passing and bending at the top of the slit compared to the bottom of the slit, those waves, when they reach the screen at a point P, those waves will have traveled a different distance. And once you get to the point where you have a difference in distance of a half wavelength or a full wavelength, then you start to get constructive and destructive interference on the screen, and you'll get these alternating bright and dark spots corresponding to constructive and destructive interference. And so waves from different parts of the slit travel different distances, and so you get destructive interference when the slit width times sine theta is equal to m lambda, where again m here is the order. So this is destructive. This is where you get no light on the screen, right, where the waves exactly cancel out. Again, this is diffraction for a single slit of width d. All right, so let's return to the double slit, and we're going to now include a treatment for diffraction. In the previous video with interference, we ignored the fact that our slits have some physical width, and so when you ignore the width of your slits, then you end up with this purple line here, just interference, an interference pattern. But since our slits have some finite width, then you will also have diffraction on top of that interference pattern. And the diffraction in this picture is denoted with the blue line. And so for this particular figure, the slit width is twice the wavelength of light, and the separation of the slits is 6 times the wavelength of the light. And so when you combine both the interference and the diffraction pattern, what you end up getting is these alternating peaks and valleys, but they are enclosed, those interference patterns are enclosed within that diffraction envelope. And so since the separation is 3 times as large as the slit width, you end up getting a missing order here. So the m equals 3 order ends up missing, because that's where the diffraction envelope is 0, even though the interference pattern is not 0 at that location. You can go beyond 2 slits to many slits in talking about diffraction, and typically when we go to a large number of slits, we approximate this as an infinite number of slits, and we call this a diffraction grating. And a diffraction grating is incredibly useful because white light that is incident on your grating is going to result in a central white peak, and then the first order, second order are going to include the wavelengths of light spread out based on the wavelength of light. Now, I'll point out this figure from the book is backwards or reversed. The pattern should go like d sine theta equals m lambda. And so what that means is that if you have shorter wavelengths like violet light, then if lambda is small, then that means sine theta needs to be small. And that means that the angle is going to be smaller. So it should actually be violet on the inside and red. So when the wavelength is longer, you need sine theta to be larger. That means a larger angle. And so the red should be on the outside in this figure. And so unfortunately, the book has it reversed here. All right, and the last thing that I want to talk about is implication of the diffraction phenomena, and that's the idea of angular resolution and the ability to distinguish in an observation or in an image, the ability to distinguish two physical objects in your image or your observation. And the idea here is that if you have two objects closely spaced, close in physical space, then the diffraction pattern of the light from those objects can overlap. And if the objects are too close to each other in physical space, then the light will overlap, and you won't be able to distinguish between one or two distinct objects represented in your image. That's easier seen down here in this figure, where I've got two objects, the light passing through some circular aperture, and then the intensities of light seen on the screen. There's going to be that standard diffraction pattern where there will be a central peak, and then there will be a first minimum corresponding to the destructive interference. And the idea is that if the central peaks are spread out far enough so that the central peaks line up with the first minima of the other source, then that's the criterion to be able to distinguish between one or two distinct sources. So this is called the Rayleigh criterion. And so it's the diffraction limit for an observation. So you can resolve two images if the central diffraction pattern is directly over the first minimum of the other. And the characteristic expression for how to quantify that is listed here, where this angle theta that you're solving for is in radians. So lambda is the wavelength that you would observe, take your photograph, your image, and d would be the diameter of the aperture. So this is for circular aperture observations. And on the last page, I have a nice comparison discussing the angular resolution, or the diffraction limited resolution, of two different telescopes. On the left, we've got the Hubble Space Telescope. The Hubble Space Telescope is a 2.4 meter telescope. The telescope is designed to observe from the infrared to the UV, and that's a range of wavelengths, but let's just say we want to characterize the diffraction limit for the Hubble Space Telescope if we observe, say, like in the middle of its capability range, so around 500 nanometers. That's roughly green light to your eye. Well, if you plug in 500 nanometers and 2.4 meters, you end up getting an angular resolution, so of 2.54 times 10 to the minus 7 radians. That means on the sky, if two objects are separated by more than that amount, then you'll be able to tell them apart in your image. And that angle, that's an incredibly tiny angle, that works out to be about 0.05 arc seconds. So an incredibly tiny angular separation. Now, compare that to the Arecibo telescope, which is a 305 meter diameter radio telescope located in Puerto Rico. Now, this is a radio telescope, observes the universe over a large range, but one of the most common wavelengths that the Arecibo telescope gets used for is to observe 21 centimeter wavelengths. So let's use that for our calculation for the angular resolution. And so the plugging into the expression, the 0.21 meters, the 305 meters, we get an angular resolution of 0.0084 radians. We get about 3 arc minutes compared to the 0.05 arc seconds. Or if you want to look at the degrees, about 1.5 times 10 to the minus 5 degrees for the Hubble Space Telescope, and about 0.05 degrees for the Arecibo telescope. The point being that the Hubble Space Telescope, even though the mirror diameter is incredibly small compared to Arecibo, the angular resolution of the Hubble Space Telescope is orders of magnitude higher, and that's because the wavelength of light that the Hubble Space Telescope observes is significantly shorter than the wavelengths of light that the Arecibo telescope is used to observe. Right? So even though the Arecibo diameter for the telescope is over 100 times larger than the Hubble Space Telescope, the wavelength that gets observed at Arecibo is way, way more than 100 times longer than the wavelength observed by the Hubble Space Telescope. And so that means the angular resolution of the Arecibo telescope is much worse. And so when you see these numbers, a larger number here means that things have to be further apart on the sky for you to be able to tell that they're distinct different objects when you take your image. So a smaller number, like with the Hubble Space Telescope, means that you can distinguish between 2 points of light on the sky that are much closer together than you can with the Arecibo telescope.